Welcome everybody to Algebra 2, Section 7.2, Solving Exponential Equations. We're going to have two different types. Set 1 is going to be with a common base, and then set 2 will be without a common base. So regardless though, you're going to use the properties of exponents to simplify each side of the equation. Rewrite the equation so both sides have the same base as needed, which won't be needed in set 1. And then step 3, once they have the same base, we're going to drop the bases and just set the exponents equal to each other and then solve the resulting equation. So step 1, problems 1 through 4, we can just actually skip to step 3, but sometimes you're actually using step 1 occasionally. So step 1 here, or number 1, as we solve the equation, 2 to the power of x plus 1 equals 2 to the power of 9. Well, since they both are 2 to a certain power, the only way for this equation to be true is if this exponent and that exponent are equal to each other. If x plus 1 and 9 are the same, then the 2 to that power and 2 to the power of 9 must be the equivalent, which must mean that x plus 1 must equal 9. And so we can drop the bases essentially and just write the exponents equal to each other. And that's something you can do whenever you have a base raised to a power equals the same base raised to a power. And now we can solve this equation by subtracting 1 on each side and just getting x equals 8. And so if x equals 8, this initial equation is a true statement. On step 2, problem 2, we have the same scenario with common bases of 5. And so since they have the same base of 5, we can set the exponents equal to each other and get 4n plus 5 equals to n minus 7 and solve this resulting equation. So I'm going to subtract n from both sides, giving me 3n plus 5 equals negative 7. And I guess I didn't like my 3 there. And then I'm going to subtract 5 on both sides, giving me 3n equals negative 12. And it didn't like my n very well here either, I suppose. Let me go back and fix that. Then I can divide both sides by 3, giving me n equals negative 4. Now move on to number 3. On number 3, we have a little bit more going on, but they're all still the base of 3. So there's a couple different ways you can approach this problem, and they're really both actually approaching it in the same way, just two different ways of thinking about it more than anything else, rather than two ways of approaching it. So since these are multiplying with the same base, that means you add the exponents. So k plus 2 would give us 3 to the power of 2k plus 2 as you combine like terms equals 3 to the power of 5k minus 1. And so now if we set these equal to each other, we get 2k plus 2 equals 5k minus 1. And so now I'll subtract 2k from each side, giving me 2 equals 3k minus 1. Add 1 to both sides and get 3 equals 3k. Divide both sides by 3. And k equals 1. Now I did mention there was another way to think about it, so the other way to think about it is you basically just go from the initial problem and do k plus 2 equals 5k minus 1. You drop the bases right away, and remembering that because those bases are multiplying of 3 and 3, that means you must add the exponents of k and k plus 2. And so you are rather than adding them initially and then dropping the bases, you would be dropping the bases, and then in your next step, you would be combining them. And then you arrive at the exact same place and continue solving. And like I said, it's just two different ways of thinking about the problem, both leading to the exact same result and doing the exact same math, just flip-flopping the order of those first two steps. I typically opt for what I did on the left, and that's what I will be showing in the rest of the video, but the way on the right is also perfectly valid, to be clear. So in number 4, multiple bases of 10, raise exponents, so we're going to add these exponents. So on the left, negative 4 plus 9 is 10 to the power of 5. On the right, if we add these exponents, we get 3b minus 7 as we combine like terms And so now we drop the base and set the exponents equal to each other and get 5 equals 3b minus 7. If I add 7 to both sides, I get 12 equals 3b. And then if I divide both sides by 3, I get v equals 4. Now, when you don't have a common base, that means we have to get the same base. And so what we're going to do is rewrite the problem to turn it into a problem that looks like this set 1. And so my advice here is to always change the base or the term, the number that is bigger and that is a fraction. So you're going to see ones that are bigger and smaller. You're going to see ones that are fractions and non-fractions. I always encourage to change numbers that are bigger and change numbers that are fractions. And so sometimes you only have to change one number, and sometimes you have to change both. Here we only have to change one. And I'll talk about when you end up having to change both, but it won't come till later examples. So for now, we can rewrite 36. 36 can be rewritten as 6 to the power of 2. And so I just leave my left-hand side the exact same. And so now, knowing that 6 to the power of 2 is the same thing as 36, so what I've written so far is mathematically valid, that in the red, this would be like a problem up above from 1 through 4, that I have bases of 6 equal to each other. And so now I can set the exponents equal to each other and get 2x minus 10 equals 2. And I can start solving the same way we did up above. I'll add 10 to both sides, giving me 2x equals 12. I'll divide both sides by 2, giving me x equals 6. Now, you could, if you wanted to, from the original part of this problem, change the other base of 6 to 36. How you would do that is this is secretly 36 to the exponent of 1/2. It's really the square root of 36, which is the exponent of 1/2. And then that is to the power of 2x minus 10 still. And so then you'd multiply this 1/2 times each of these, and you end up getting 36 to the power of x minus 5 equals 36. And so we set these exponents equal to each other, so it's x minus 5 equals the invisible 1 on 36. And then we add 6 to both sides, giving us x equals 6. The same exact answer. And the reason I typically avoid this one is because it does lead to fractions more often, and sometimes they don't work out very cleanly. They did here, thankfully, but sometimes in our in-between steps, they don't work out very cleanly. And so to avoid that, changing the bigger base to a smaller base is a good way to go. And once again, what I will always encourage and what I will do. So on number 6 accordingly, I will say, hey, the bigger number is 8. I will change 8 to become 2 to a certain power, and it is 2 to the third. So I have 2 to the power of p minus 7 equals 2 to the third, and now I can set these exponents equal to each other since I have the same base on each side of the equation. And so I get p minus 7 equals 3, and I will add 7 to each side and get p equals 10. Moving on to number 7, I said the other time I would change a base is not only the bigger one, but also fractions. And so 1 over 7 I would change. I would change 1 over 7 to 7 to the power of negative 1. Because remember, negative exponents just tell you to reciprocate it. And then the other exponent can, the other exponent can just stay the same because it's already a base of 7. So now we have the same base or common bases, and we can set the exponents equal to each other. 4x plus 11 equals negative 1. So if I subtract 11 from both sides, I get 4x equals negative 12. Divide both sides by 4. X equals negative 3. Moving on to 8. 32 is equal to 2 to the power of 2n minus 9. So 32 is bigger. I will change that to 2 to the power. That is 2 to the power of 5. and that is equal to 2 to the power of 2m minus 9. And because now these are common bases, I can set the exponents equal to each other and get 5 equals 2m minus 9. And as I begin to solve this, I add 9 to both sides, giving me 14 equals 2m, and divide both sides by 2, giving me m equals 7. Then I'll move on to number 9. I'll change my bigger base, which is 27 here, even though it has an exponent other than 1. That's fine. I'll change it to 3 to the power of 3, and I'll have to put that in parentheses with 2x plus 6, the existing exponent, outside. Because 27 was raised to a power, so 3 to the third is 27, also raised to a power. And so now I'll have to distribute this 3, or the 2x plus 6, to the 3, however we think about it. Either way, the 3 multiplies with both 2x and 6. And we get 3 to the power of 6x plus 18 equals 3 to the power of 2x. And now, since we have the common basis of 3, we can set the exponents equal to each other and get 6x plus 18 equals 2x. Subtract 6x from both sides here in this case to get it away from the 18, even though it's the bigger x. I'll get 18 equals negative 4x. And we're going to get a fraction here in our final answer, and that's okay. Divide both sides by negative 4. And we end up getting x to equal negative 9 over 2, or negative 4.5, or negative 4.5. However you write that is fine with me. And wherever the negative is on this fraction is also fine. On number 10 here, I'm going to change that 16 since it's bigger. And so the left side is going to stay the same. The right side will become 4 squared to the power of y minus 3. And so we have 4 to the power of y plus 2 is equal to 4 to the power of 2y minus 6 as we distribute the 2. And so I get y plus 2 equals 2y minus 6. And I'll subtract y from each side, giving me on the right y minus 6, on the left 2. Add 6 to both sides, giving me 8 equals y. Now I'll move on to the next page. Number 11 here. This is where I have to start changing both bases. The reason I know I have to change both bases here is because 25 to no power, or to no integer power, is 125. It'd be a fractional exponent. And in this case, you would have to have a number other than 1 for both the numerator and the denominator, and it gets quite messy. So it's cleaner to change both bases. And the same thing's true for 25. No integer exponent, non-fraction, would give you or turn it into 25. And so if I changed, so I could say, okay, what could be raised to a power to get both 125 and 25? And the answer is 5. So it becomes 5 to the third to the power of y and 5 squared. And so this becomes 5 to the power of 3y as we multiply 3 and y, and 5 to the power of 2. And we set those equal to each other, the exponents, and we get 3y equals 2. Divide both sides by 3, and our answer is 2/3, aka 0.6 repeating. Number 12, we face the same scenario where 16 is not 8 to a certain power, and 8 to a certain power is not 16, but rather they're both 2 to a certain power. And so 2 to the 4th power is 16, and then that would be raised to the power of 3x, excuse me. And 2 to the 3rd power is 8, and that'd be raised to the power of x plus 2. And so on the left, you get 2 to the power of 12x as you multiply those exponents. I wrote x in the wrong place, and then I wrote it twice. And on the right, as you multiply the 3 to both exponents there, are both parts of the exponent, I should say, you get 2 to the power of 3x plus 6. And so now we can drop the bases and get 12x equals 3x plus 6. And so now if we subtract 3x from both sides, we get 9x equals 6. Divide both sides by 9. and this reduces to 2 over 3, which was the same answer as last time, neatly enough. Coincidentally enough. On 13, again, we have to change both bases because 4 to no power is 8 and 8 to no power is 4, but they're both 2 to a certain power. So, I guess just zoomed me back a page and zoomed me out for some reason. So 2 to the power of 2 is 4, and that's to the power of 3x. 2 to the power of 3 is 8, and that's the power of x minus 1. On the left, we multiply those exponents and get 2 to the power of 6x. On the right, we multiply the 3 to both the x and the 1, and we get 2 to the power of 3x minus 3. And now we can set those exponents equal to each other. So we get 6x equals 3x minus 3. I subtract 3x from both sides and get 3x equals negative 3. Divide both sides by 3. I get x equals negative 1. On 14, personally, I would personally actually change both the 81 and the 1/3. You could, if you prefer, just to change 81 to 1/3. That would also work. Either one's a perfectly fine option. I'll just showcase both here, and how they end up giving us the same resulting answers at the very end. So if I change 81 to 3, for example, that'd be 3 to the power of 4 to the power of 2x plus 5. And if I change 1/3 to 3, that'd be 3 to the power of negative 1 to the power of 2x. And so on the left, it gives me 3 to the power of 8x plus 20 as I distribute those exponents. And on the right, I get 3 to the power of negative 2x. And I can set these exponents equal to each other. 8x plus 20 equals negative 2x. If I subtract 8x from both sides, I separate my x's and my constants, and I get 20 equals negative 10x. Divide by negative 10, and I get x to be negative 2. Now on this one, you actually could have just changed one base, like I mentioned. We could just change that 81. And what you would do is you would change it to be, instead of 3 to a power, it'd be 1/3 to the power of negative 1/4. But note here, you would need a second set of parentheses because you need to clarify that's not just the 1 raised to the power or the 3 raised to the power, but rather the whole fraction. And then raised to the power of 2x plus 5. And then equal to 1/3 to the power of 2x. And the only thing that changes here is that negative exponent. That wouldn't be negative 1/4, my apologies. That'd be negative 4. I don't know why I did that as 1/4. It's not the 4th root. Let me go back and fix that. Negative 4, that's better. And then I multiply this negative 4 to each of these exponents. And so I get 1/3 to the power of negative 8x minus 20 equals 1/3 to the power of 2x. And now we can set these exponents equal to each other. And you'll notice that it's actually just the exact opposite signs from what we had originally. It's as if you just took that equation and multiplied everything by negative 1. And so if you end up solving this, you'll still get the exact same answer of x equals negative 2. You'd end up dividing by positive 10 in just a moment after you add 8x both sides and getting negative 1 divided by positive 10, which is negative 2. Number 15. 8 to no power is 32, and 32 to no power is 8. But they're both 2 to a power. 2 to the 3rd is 8, and that'll be raised to the power of 2a minus 1. And 2 to the 5th is 32, and that'll be raised to the power of 2a plus 1. And so on the left, we get 2 to the power of 6a plus 3 as we multiply those. On the right, we get 2 to the power of 10a plus 5 as we multiply those. And then we drop the bases and set the exponents equal to each other and start solving. So I subtract 6a from both sides, and on the left I'll get 3, on the right I'll get 4a plus 5. Then I'll go ahead and subtract 5 on both sides and get negative 2 equals 4a. Then I'll divide both sides by 4. I did something wrong. What did I do wrong? Oh, I see my error. My apologies, y'all. Let me go back and fix this. This should have been a negative 3 way up here. Make it obvious, because this was a negative 1 multiplying with 3. Meaning this was a negative 3, this was a negative 3, making in the pink, instead of a negative 2, a negative 8. My apologies for that error. And so now as I do negative 8 divided by 4, I get negative 2 to equal a. Moving on to number 16. 27 to no power is 243, and the same is true in reverse, but they are both powers of 3. And so 3 to the power of 3 is 27, and that would be the power of 2x. And 3 to the power of 5 is 243, and that's raised to the power of x minus 2. If you're having trouble finding, like, what would I be raising to a power, like what base do I change these to? Start with the smaller one. It's easier to find that with the smaller one because there's less numbers to choose from. And then just start spamming in your calculator. You know, like 2 to different powers, and then you'll notice you get pretty big and you skip 27. And then 3 to certain powers and you hit 27. So it's, oh, it must be 3 to the third. And then after you find 3 to the third, okay, well, now I'll try 3 to a certain power and see if I get 243. And eventually, as you keep multiplying by 3s, you get 243. And so now we'll multiply these exponents and get 3 to the power of 6x equals 3 to the power of 5x minus 10. And set the exponents equal to each other. 6x equals 5x minus 10. Subtract 5x from each side and get x equals negative 10. Number 17, we have multiple 4s on the right-hand side. And so on the left-hand side, we need to change it to 4 to the third, first of all, because that is a power of 4, and these are already 4s. And this is what the same thing we did earlier, where we can do 1 and 4x. So we add those and get 4 to the power of 1 plus 4x. And now we just set these exponents equal to each other and drop the bases. 3 equals 1 plus 4x. So it's combining what we did on problems 3 and 4 at the beginning of the notes and the end of set 1 with what we were doing here in set 2 of changing bases. And so now as I subtract 1 from each side, I get 2 equals 4x. And I divide both sides by 4. And I get x equal 1/2. Moving on to number 18 here. 81 is the power of 9, so we don't have to worry about changing these bases, but we do need to combine them into one base, so I'll add those exponents. And as I combine like terms, I get 4x plus 4. On the right-hand side, I'll change 81 to the power of to 9 to the power of negative 2. 9 squared is 81, and the negative just reciprocates it or flips it. And now I can set each exponent equal to the other. 4x plus 4 equals negative 2. And I'll subtract 4 from each side, giving me 4x equals negative 6. Divide both sides by 4. And x equals negative 3 over 2. And that is my answer. You could also call it negative 1.5 and negative 1.5, you know, those would also work. Number 19. So more base changing going on. We have a base of 7, 49, and 1/7. Well, they can all be 7 to a certain power, and this last one already is 7 to a power, but the first two are not. So 1 over 7 is 7 to the power of negative 1. 49 is 7 to the power of 2, raised to the power of x minus 5, times 7 to the power of x minus 9. Next, we'll have to finish multiplying these exponents together. Then we can combine these into one base. And so the left side is just going to chill and just keep being rewritten for a moment. And so on the right, we're going to get 7 to the power of 2x minus 10 times 7 to the power of x minus 9. And then we're going to combine like terms on the right for those exponents and get 7 to the power of negative 1 equals 7 to the power of 3x minus 19. Now that we finally have 7 to a power equals 7 to a power, the same bases, we can set the exponents equal to each other. Negative 1 equals 3x minus 19. I'll add 19 to both sides and get 18 equals 3x. I will divide both sides by 3, giving me x equals 6. Last problem of the day. 4, 16, and 4. Well, 16 can become a power of 4, so we'll keep the first and third bases. So 4 to the power of 2x. 1 over 16 is 4 to the power of negative 2. And then 4 to the power of 6x plus 18. Combine these by adding the exponents. There's no like terms to combine. So it's just 4 to the power of 2x minus 2, or plus a negative 2, equals 4 to the power of 6x plus 18. And then we can set those exponents equal to each other. 2x minus 2 equals 6x plus 18. Subtract 2x on both sides, giving me 4x, plus 18 on the right, negative 2 on the left. Then we will subtract 18 on both sides, giving me negative 20 equals 4x. Divide by 4 on both sides, and x equals negative 5. And that's my answer. And that wraps up section 2 of Unit 7 for Algebra 2.